A very good afternoon to all of my students present. Today we will do a basic introduction of energy band in semiconductors. Those who have just passed 12 may have this fresh in their memory that materials, how are they defined and how are they distinguished based on their energy bands and their various elements properties. So let's begin. Myself, Deepak Sahu, and I'm an assistant professor in Electronics and Communication Engineering Department in IIMT College of Engineering, Greater Noida. So let's start a basic introduction. So basically, we will begin with the definition itself. As to what is an energy band. Now, apart from the these definitions, we will try to make our limit and constraints to more or less on the physical aspect and the physical relevance of this system rather than standard definitions. So, since energy band diagrams mainly deals with the energy variation from to that of conduction band and valence band, so energy can be basically defined as a range of energies available. Now, when we are using the term range of energies, it is not any type of continuous energy pattern, but rather than a discrete energy patterns where a particular level has a fixed set of energies which it can hold. So coming back to this basic definition, the range of frequencies that an electron will possess in an atom is known as energy bands. Now, three basic parametric elements are there in energy bands description. First is valence band, second is conduction band, and the energy gap between them, which is primarily known as forbidden energy gap, exists between them. Now, moving further, this is the basic layout of an energy band. Now, since these all are running at microscopic level, so temperature plays an important role. So wherever we will define this energy, we will take a clearly look of energy patterns that exist at a particular temperature. For example, here, the very basic elementary description of energy bands is given here. With the topmost band pattern is known as conduction band, having at its lowest most point energy of conduction, and the bottommost energy pattern is the valence band, which has its topmost point energy level at its valence band energy level. Now, the basic characteristics at 0 degree Kelvin is defined here, which we can clearly see that a temperature below room level, there are no conductivity signs or patterns available, since there is no type of thermal or external energy agitation available. So all the electrons which are primarily in the valence band are connected in the covalent bond structure with its neighboring atoms. And so there are no free electrons available for any type of electrical conductivity in the conduction band. Now, another descriptive view is shown here, in which two parametric elements are being shown in the same energy band diagram pattern. One is little shown with the blue line, which shows increasing electron energies, and another is a red line, which is decreasing downwards. by arrow and showing increased voltage pattern. Now let us break these two and try to understand what exactly these arrows signify. So as you know that energies are a particular set of values, being continuous in nature, then to they have a discrete energy patterns, which any particular shell can hold. So whenever any external energy source, which can be in the form of thermal agitation, radiation, or electric field, comes and is absorbed by the Valence band, the energy of that particular shell increases beyond its beholding capacity, which results in a random breaking of bond and ejection of electrons. Now, the valence band, all the energy is stored in the form of potential energy. So wherever this extra energy comes, so when the electrons releases to maintain the original energy level, this ejected electrons holds kinetic energy. And with this increased kinetic energy, this free electron goes to conduction band level. So we come by the definition, we see that conduction band is the lowest energy state for electron. In the same way, valence band is the showing as a high energy state for filled outer shells. And EG, as usual, a difference between conduction and valence band. In here, we have taken example of a semiconductor based on silicon, and its value is 1.2 electron volts, which is the primarily unit to define. Now, a more thorough description of energy bands is being shown here in the form of basic definitions, like valence band primarily, which is the bottommost point band pattern in an energy band diagrams of a particular item. First point is the most important point here. When there is no type of thermal agitation available, in this energy band, there are a large number of electrons, but there are no electrons available at this point. Since valence band is closely connected to the nucleus of atoms, and conduction band is a temporary state for any free electrons, whereas the valence band shows a permanent state, which shows the most stable kind of electron patterns. So that's why it's written there that this band contains very large number of electrons, because mainly all electrons are concentrated in valence band. These valence bands, which is obvious, will never get empty. But it's the third point. There is a major disadvantage is mentioned. I would not rather say it's a disadvantage, but a limiting value. Without thermal stations, these electrons cannot by themselves absorb energy and go or move to the above energy higher levels. Now, second is the conduction band pattern, in which the density of electrons is only available when there is a free electrons which is being broken from the valence band and is freely available to conduct. Now, its comparison is mentioned as comparison to the valence band energy level. These electrons can gain energy from the external field or any type of electric field, which can be in the form of thermal agitation, a battery supply, or any form of electromagnetic radiation. Now, third is the forbidden band or energy gaps. No electrons are permissible. They are only taken as a conductive medium or other than a prohibited space which electrons has to jump. They even cannot continuously flow, they have to eventually jump, which concludes our earlier deductions that energy is being continuous, does not flow in the continuous form, but rather exist in a discrete nature. Now, we come to the basic three categorizations of materials, which are primarily metals, insulators, and the newest member being added is a semiconductor. Now, insulators are clear that their electrical conductivity is 0, and metals are electrical conductivity very high. But semiconductor is a little bit mysterious, because at normal conditions, it works and behaves as an insulator, whereas Some intentionally reduced conditions are inserted inside them. They under desirable or most obvious conditions will show electrical conduction. So, the major definitions or whole cheese is related with the electrical conductivity that exists inside a material. So now as a basic general value is given of a metals and insulators, which can clearly see that why metals are highly conductive. But semiconductor, as we have earlier discussed, is a mysterious element which under some conditions will behave as an insulator and under some conditions will behave as a metal. So that's what it makes it so versatile, because it shows two different variation of properties. Now there is a electrical band conduction level is being shown that at normal room temperature or low temperatures where there is no thermal agitation available, valence band is fully filled since it is mainly attached to the atoms, whereas conduction bands withholds electrons only when free electrons are available. Since non-free electrons are available for conductions and at normal or low temperature, empty conduction band is shown and full valence band is shown. Now, since conductivity is more or less related with the electrical property, now to have a material shown any type of electrical property, it is necessary that some electrons has to be available in the conduction band if it has to show any type of electrical conductivity. Now, if due to any medium, the valence band absorbs energy, then its topmost or its outermost shell, since it's discrete in nature, can only withhold a fixed amount of electrons, which could contribute for conduction. So, now in diagram, it is clearly seen that innermost valence shell does not participate in providing any type of free electrons. So in here diagram, in the rightmost point, the topmost shell, which has energy form such as EV, now valence band topmost energy level is VB, which shows electrons available, which could only participate in conduction. Now, since here that as soon as one electrons move by the provision of an exchange energy, the electrons, after gaining sufficient energy, will move in the conduction band, leaving behind a vacant space. Now that vacant space is a region void of electronic charge. So it's an hollow space which constitutes opposite nature, same value charge. Now as you can see that electrons, as we keep on moving, so conduction band getting filled, and points noted there that bottommost point only gets filled first, then its uppermost points. Whereas in valence band, topmost points get vacated first and holes are created, whereas innermost are created later. So finally, we have seen that 4 electrons have jumped through the conduction band and 4 vacant space in the form of holes are created. Now, since p-n junction dot, they are both a type of carriers, p and n type. So we can say that holes band contribution to current shows movement in valence band, whereas electrons when shows or contribute to current shows movement in conduction band. Since hole is a massless quantity, it cannot go to the conduction band for conduction, so it resides mainly in the valence band. Now, here issue is that as we have long spoken of conduction levels, so what type of energy systems could provide thermal agitation? So basically, we are mainly dealing with thermal energy, electric field, and electromagnetic radiation. Thermal energy could be Due to the continuous working of a circuit in which device is put, electric field can be from the external device and radiation can be from the nearby space or the device itself. Now the thermal energy is basically defined and its excitant rate is given by the given formula. So as we can clearly show that in spite of being very low, 25 millielectron volts, it is a sufficient energy which can make electron jump to the conduction band. But all listeners must note that conduction band is not a permanent residing state for any electrons. If electron is free and it jumps to conduction band, it can reside only for a few time, depending upon the latency rate. Then it has to return back to its base level. Or if energy is very high, then while returning to the valence band, extra energy will be radiated in the form of light or any other patterns. Now, for as well as electric fields are concerned, for low electric fields, as per depending upon the alloy based on silicon and germanium, we have to observe and show that electrons can jump or not. For example, it is here mentioned that if an alloy is a gallium arsenide or silicon, low electric fields does not have enough power, so that they could make electron jump from valence band to auto. So little high bit of energy is required here. Now, thermal radiation is an electromagnetic wave. So basically, any wave deals with frequency and wavelengths. So for silicon, wave motion is given by 1.1 electron volt. And the wavelength, if it is in the form of electromagnetic radiation, would be enough 1.1 micrometer to make this jump. So we can say that if a material is made from silicon, and LE, light pattern or electromagnetic pattern, which has wavelength greater than 1.1 micrometer, would be enough to make the electron jump from valence band to conduction band. So that's how it goes. Now, that was I'm talking about. The conduction band is actually not a permanent residing state for any electron, not a permanent excited state. So you can clearly see here that electron, after getting thermally agitated, jumps to a conduction band, then after some time it returns back, because conduction band is not a permanent residing state for any electron. So while returning, if its energy is not used or wind up, the extra energy will be retained in the form of photon, which is the primary intention made pattern for light sources like LEDs and lasers. Now, insulators, as we can show clearly in the diagram, they will never have any free electrons available in the conduction band. So, since because the energy required to make electron jump from valence band to non is very, very high. So, in providing this energy, electron can or jump, but the basic crystalline structure of a system will get melt down due to this high energy levels. Now, in metals, it is clearly shown that there is no need to jump from valence band to conduction band, since forbidden energy gap is not present here, and conduction band and valence band are merged actually. So valence band has to not jump, it can easily move to the conduction band, and when conduction removes, it can easily come back to the valence band. Now, this is a basic structure in which shows a nucleus, and from inner to outer shells, it is a silicon-based system which has 14 electrons. So energy bands shell in the form of shells are mentioned, innermost 2, then 8, then 4 as per electronic distribution. This distribution is based on temperature at 0 degree Kelvin, in which it clearly states that outermost shell has 4 electrons. Now, this is the more concise or compressed diagram form, in which a silicon outermost shell is shown, and this is the lattice structure. Now, in the next pattern, bonding is complete at temperature equal to 0 degree Kelvin. double covalent bond is made, and each silicon crystal gets attached to its neighboring atoms and completes the bond. Now, if by any form thermal station appears and valence shell gets energy more than its required or contained energy form, this extra energy, as shown in the diagram, is provided at valence band and result with electrons take this energy in the form of kinetic energy and jumps to the conduction bands. So you clearly see both the diagrams that square space between silicon atoms represent the conduction band, and you can clearly see how electron moved in the right and left diagram. You can clearly see that how electrons move in the square space. Students clearly see as electron moves and bonds breaks, this primarily we have taken as intrinsic material in which all atoms are silicon. So bonds keep breaking in the left diagram. In the right diagram shows that electron move. So in intrinsic material, by providing external energy source, this is how electrons are released. And since it is intrinsic material, so bond breaking and electrons condition, it will always be in pairs. So we can clearly see electrons are released, bonds are broken, and this pattern completes as per the energy available provided to the crystal. So electrons randomly move in the conduction space. Okay, so this is a basic pattern. So I think this is enough for the introductory part. And in the coming lectures, we will take more advanced topics regarding this. So students, that is for now, and we can clearly conclude our lecture here. Thank you for listening. Thank you, students.